Hey there. This is going to be the final project for the Stellar Robotics 2018 CAD class. What we're going to be working on primarily is we're going to be working on designing the frame of a sheet metal drivetrain. Now, I believe it's going to be kind of based on how much time we have, but I believe we're going to try to model a whole drivetrain. But the primary purpose of this class is, or this project, is to get a little more practice with sheet metal and learn how we use sheet metal in a really practical situation like on our drivetrain. This here that I have on my screen is Stellar Robotics' 2018 drivetrain from our robot Arcturus. This is a pretty good idea of what we're going to be modeling. We're going to simplify what we're working on quite a bit. We're not going to, we're not going to put shifting gearboxes in it. We'll probably just do a really, really simple single-speed 2-sim gearbox. But that'll be like one of the last things we do. We're not going to be doing this like angled surface in the front. It's just going to come down to a sharp corner. The only reason that we did this was because we had to go up on a ramp, and having that corner not there helped with clearances somewhat. We're going to be doing a 6-wheel design, not an 8-wheel design, and we're not going to have this notch in the front. Both the front and the back will look more like this. In addition, let's see what other differences. There's going to be a lot of differences, but we're not going to bother putting a battery box or the encoders in there. The other thing, we're going to go ahead and model a belly pan because it's going to end up being pretty integral to the structure. However, it's not going to be raised like this, so the middle of the robot will be flush with the bottom of the drive rails. Okay, all differences aside, let's talk about exactly what the structure of this actually looks like, the important bits. So the important thing is we have these pieces here called drive rails. Now, this is the outer drive rail. This is an inner drive rail, what we call them. The inner drive rails are slightly different just because they have to have mounting holes for the gearboxes. Other than that, they're pretty much the same. The drive rails are made out of 1/8-inch thick aluminum, and basically we tap the 1/8-inch thick aluminum, which is kind of a sketchy thing to do, but we've gotten away with it for 2 years now without any issues. Basically, we tap the aluminum 1032, and then we just bolt these bearing blocks to it. Now, the advantage of doing that is this bearing block has, well, it's kind of hard to see. Basically, there's a 16th-inch plate here, which is just a spacer, and there's 2 1/8-inch plates. Basically, the 16th-inch plate acts as a spacer for the flange of the bearing, which is facing in. So basically the front of the bearing with the flange is just smashed up against the plate. It's not smashed, it's actually not tight, but it's up against the plate. This spacer gets us out over the flange, and then these 2 plates here are actually the bearing blocks. The only reason this is 2 plates instead of 1 piece of 1/4 inch is just because the equipment that we use isn't capable of cutting 1/4 inch. That being said, I think that's going to change in this next season. So in this drivetrain, we're going to design this as being 1 piece, and then the spacer, of course. Basically, the reason for this weird bearing block arrangement is that we can unscrew this bearing block from the outside of the robot, and then once we do that, this shaft can pull straight out the side of the robot, which means we can drop the wheels out the bottom and stuff. Makes it super maintainable. We ran this setup for the first time 2 seasons ago, 2017, and we were able to do a full wheel swap and everything at championships, changed spacers and stuff around pretty easily. And then obviously on the inside drive rail, we don't need to be able to pull this bearing block from the from this side, so it's just bolted to the inside. The important thing is you'll notice the flanges are facing the same direction, which is important. Let's see, what else did I want to talk about here? Just to note how we're driving the the wheels with, it's a piece of hex shaft, and then we've got these pulleys and belts. We're going to do the same thing, except it's going to be 6 wheels. So basically, we won't have this shaft, won't have this belt, and basically instead of this sprocket, or I'm sorry, pulley, we'll just have a space here. Yeah, so the other important thing to note is this front piece, which is not 1/8 of an inch. I think next season, this is somewhat unrelated, but I think next season what we're going to try to do here for these plates is we're going to make them 1/16 to save on weight, because 1/8 inch really is overkill if you design it correctly. If you put some pieces that are kind of inside these drive modules to stiffen it up, you can use 1/16 for this stuff if you know what you're doing. We ran a full 1/16 inch thick sheet metal drivetrain in 2016, and if that frame can survive that game, then 1/16 inch will work for any game that you put it through. You just got to be kind of careful about what you brace and where you put your flanges and stuff. Yes, but we're going to model this one 1/8 inch like we usually do. However, in the upcoming season, we may switch to 1/16, and then instead of tapping holes in here, we're going to just press some studs in, but I'm not going to get into that. But the front rails are 1/16 just because they don't need to be 1/8 for rigidity. If we're super, super worried about high-speed collisions, then you might want to make these thicker just to take an impact. That would be like a really wide open field like 2014 or maybe 2017. Yeah, so the big thing I was talking about here, I got sidetracked there, but the big thing here is that this kind of front channel, this is actually the back, but it'll be the front and the back on our design, is it kind of wraps around the drive rail, and that's important. The drive rails kind of stick inside, and then the belly pan kind of tucks up underneath the inner drive rails. It's not like that here because this belly pan's kind of a weird arrangement, but on our design it'll be on the bottom of this one. So alright, so we're going to model our drivetrain 31.5 inches long and 25.5 inches wide. Those are just numbers I pulled out of the air, but they're kind of about the size that we're making robots these days. 2017 was obviously way, way smaller, but that's pretty typical. So here's what we're going to do. We're going to start with a sheet metal part. This is going to be our outer drive rail. We start with the outer drive rail. This is how we figure out our wheel spacing and all of that stuff. So we're going to start with the rectangle here. All right, so this is going to be our drive rail, right? We're going to have flanges all around 4 sides, and then the front channel will wrap around the drive rail here, and the back channel will wrap around the drive rail in the back. Now we know the drive rail, or I'm sorry, we know the end caps, those 2 end channels. We know those are 1/16 of an inch thick, and we know we want our robot from front to back to be 31.5 inches long. So basically, we've got a 1/16 of an inch on the front and a 1/16 of an inch on the back that's not accounted for in the length of the drive rail. So basically, we've got to take those off of the length of the drive rail to make our drivetrain the right length overall. So basically, we want the drivetrain to be 31.5. We've got to subtract a 1/16 for the front and subtract a 1/16 for the back, and that will be the length of our drive rail. For now, I'm going to make this 4 inches tall. I think that will work. We might make it a little taller, a little shorter. We might go to 3.5 actually. The actual in-person CAD class is over. However, so we started working on this project already, so I'm kind of redoing what we already did in the class, and I think we ended up with this being 3.5, but I'll show you guys how to actually model that and figure that out in the CAD software. Okay, we're going to use 4-inch wheels. I think we're just going to use some wheels from Vex. So we're going to model 3 construction circles, just kind of throw them down randomly. Yep. Okay, now on 6-wheel drivetrains, the middle wheel is always lower than the outer 2, and the reason for that is you don't want you want more of your weight on the middle wheel than on the outer two wheels, so that when you turn, there's not as much load on these wheels, which means there's less friction and your robot turns easier. Okay, so we need to kind of do a thing here. So we're going to take a construction line. We're going to connect the two outer wheels. The two outer wheels are going to be even. It automatically placed a horizontal constraint, but if it doesn't do that, you're going to want a horizontal constraint on this line. Then we need to find the midpoint of this line because we want the middle wheel to be right in the middle of these two. However, we're going to start with a line because we want the middle wheel to be below this line. So we want it to be centered on the line, but we want it to be below it. So our middle wheel's lower. So we're going to find, there's the midpoint, find the green dot. We're going to connect a line. It's okay if it's at an angle. Okay, so we got this line here. Now we got to make that vertical. All right, so now this wheel is locked in the middle of these other two, but it can move up and down as it needs to. So we're going to make our middle wheel 1/8 of an inch lower than the other two. That's fairly typical. Sometimes, depending on what we're doing, I might want to go a little bit more than that. Most people don't like to go more than this, but it seems like we're always having trouble with our robots turning. We're not putting enough drop center. So, but this is what we're going to go for. This is a pretty common value, 1/8 of an inch. Okay, so now we're going to line this center point up with this point with a vertical constraint to center our center wheel. So now our wheel is centered left to right underneath the center point of our drive rail. So now we've got these two guys that can move in and out. We got to figure out where these need to go vertically, where these need to go horizontally. All right, so let's talk a little bit about our end channels. Let's take some construction lines and let's actually draw an end channel. Okay, so this is representing our end channel. We're going to need to dimension this so it's actually the right dimensions. So let's do collinear constraint, which is the second one. We're going to pick this little end line and that little end line. That basically just lines those up. Then we're going to take a dimension. We're going to dimension between that top dotted line and this one, and that's a 1/16 because it's a 1/16 inch thick. There to there is also a 1/16 of an inch. I'm just going to click on that other dimension and click enter, or press enter. That's a 1/16 of an inch. I'm going to click on that dimension and press enter. Basically, that makes all three of these dimensions, or these two dimensions, equal to this dimension. All right, so now from the end of this part to the outside, which is this dotted line, that's going to be 2 inches typically. And this one, because I lined this little line and that little line up earlier, they won't move. So basically, this channel is going across the full width of our robot. So our wheel can't hit this, right? Here it's interfering, here it's not interfering. We want to give ourselves a little bit of a gap. Now, I'll let you guys on a little bit of a secret. It's not really a secret. Anyways, we're probably going to end up putting our wheel somewhere here, and then we're going to actually notch the end cap, because otherwise we end up using up too much length of our drivetrain just giving this room, and it doesn't really take that much strength out to notch it. So we're probably going to go somewhere in there. I wouldn't want to go past halfway, because then you start taking out a considerable amount of strength, but it's okay being overlapped a little bit. So basically what we need to do is we need to figure out the center distance from here to the middle wheel. Now, this is going to be driven by our belt, right? We're going to have a pulley on the center shaft. The center shaft is going to be driven by the gearbox, by the way, just directly out of the gearbox, driven to the middle wheel. We're going to have a pulley on the middle shaft, and that pulley is going to have a belt on it, and the belt is going to connect to another pulley on this shaft here, and then the same arrangement for the back. So basically, the center distance between the center to center distance between the center wheel and the two outer wheels are the critical dimension that we have to hold, because that's going to be based off of the pulleys that we use. Okay, so let's go to Vex Pro. We're gonna have to look at what our selection is here, like we usually do. All right, so we're going to go to belts and pulleys. They're going to be HTD because the tiny GT2 would not be strong enough. And there aren't larger GT2 sprockets available for hex shafts. So we're going to look at sprockets here, open that in a new tab, and then we're going to use 15mm wide belts because we got to transmit a lot of power through these. All right, so going back to the pulley tab here, we don't want 9mm pulleys. We want these pulleys that'll work for 9mm or 15mm. We've got 18, 24, 30 tooth, and 36 tooth. We usually use 36 teeth. You could use 30 teeth. Basically, you want to use the largest sprocket you can because that spreads the load out. You basically have more, the belt teeth basically have more mechanical advantage, and so there's less, for the same torque, there's less load on the teeth with a larger sprocket. So I am just going to verify that real quick here. I just want to make sure we use this size, whatever this size is. Yeah, 36. That's what I thought. Okay. So, like I said, 36 teeth. So we're gonna just download this real quick. CAD files. And 36 tooth, 15mm wide. That is, yeah. All right, download that. All right, leave that up. Okay, so let's figure out a belt. So we're going to open up a new tab here. We're going to go to SDPSI, my super old Chrome background. Okay, so we're going to go up to Design Tools. Come on. And go to Center Distance Designer. We've used this before. All right, so our units are going to be metric. Our pitch is going to be 5mm HTD. They're going to be two 36 tooth sprockets. Okay, so now we got to go back and we got to figure out what belts we have available to us. When we did this in the CAD class, I feel like we used like 170 teeth. Let's punch in 180 teeth. We'll see what that gives us, and then we'll try, if that's too long, we'll try 170 and see where that gets us. So 180 teeth. So if we know the center distance that we want, we can type it in here. If we know the belt that we have, we can select it down here. So we know we want 180 teeth, so we'll scroll down. And that gives us 14.1732, or 360 millimeters, which is probably an easier dimension to deal with. Okay, now I'm actually gonna do a little example here. So if I have a line, let's make this not construction. Okay, so if I dimension this line, right, it's going to create a horizontal dimension or it's going to create a vertical dimension. Now, what if I want to actually dimension the aligned length of this line? How do I do that? Well, I right-click, I click Aligned, and now it's lined up. Now, I can do the same thing if I have 2 points, right? It wants to do a horizontal or vertical dimension, but if I want an aligned dimension, I can right-click, click Aligned, and then I've got my dimension. So we need to do the same thing. Now, this middle wheel is only lower by 1/8 of an inch, right? So it's not a very, the belt won't be angled up very much going from the middle wheel to one of the outer wheels. However, it will be angled, and we want to dimension this correctly. So we're going to pick the dimension tool. We're going to zoom in. We're going to pick the center point of the circle, which is the bottom of this little 1/8 inch line. So we're going to pick that. Then we're going to come over. We're going to pick the center point of the outer wheel center. Now we know that this is wanting to give us vertical dimension, or horizontal dimension, or vertical dimension, but we want an aligned dimension. You know, it's very slight angle. The value changed a little bit. There we go. Okay, so this was 360 millimeters, and yeah, that's what I thought. So the wheel's just way too big. Or the belt's just way too big. It moves the wheel out too far. So let's go back and let's try 100 and what was it, 70. 170 is the next one down, so we'll go to drop down list, pick 170. Now it's 335 millimeters, so let's punch that in here. 335 millimeters. Okay, that moves the wheels in. Actually, that might not be right. Let's try 160, and let's try the next one down. 310. All right, go back to Inventor. All right, we'll leave it there at 160 for now. We've got to figure out where the wheels are vertically, right? If they're up here, then we'll move it out to the 170. But if they're down lower, all right. So basically, we've got a bearing block on here, and we've got a flange on the bottom of this. And really, I'm just going to open up the drivetrain model so I can show you guys. In most of the CAD classes, I've tried to kind of not, or like the videos that we've been doing, I've been trying to not show the finished product, but it's helpful in this case. Now, this used fairly large wheels. These are 5-inch wheels. They're custom. They were a nightmare and caused us problems all season long. Our custom wheels in 2017 weren't a big deal. They were beautiful, but these for some reason just didn't want to go together right. Okay, anyways, so we've got this flange here at the bottom of the drive rail, and we've got this bearing block. Now the bearing block is, I believe, 1.5 inches. 1 5/8. We're going to make it 1.5 inches though. Yeah, it can be smaller than this. Okay. Can it? Yeah, okay. We'll be fine. All right, so basically, we're going to have this bearing block, and ideally, we want our wheels as low as we can get them. I mean, we want our wheels as low as possible so we have ground clearance within reason. Now, that does affect center of gravity, but we can also make the drivetrain shorter, right? We haven't actually decided what this dimension is going to be yet. However, if we go too low, our bearing block is going to start to hit this flange. And actually, we have a bigger issue. Because this is bent, there's a radius in here. And so if we go too low, this bearing block will start to hit that radius. Now, we kind of know what we know about what this radius is, but we like to give ourselves a good buffer. So we're just gonna make sure that the bottom of our bearing block is 3/16 of an inch off the inside of this flange, and this flange is obviously 1/8 of an inch thick, so it's going to be 5/16 of an inch from the bottom of our drive rail, which is what this bottom line of this rectangle represents. It's going to be 5/16 of an inch from the bottom of this to the bottom of our bearing block. So let's we're done with this for now. I'll close that. All right, so let's draw a center point rectangle that is 1.5 by 1.5, just a construction rectangle, and let's dimension from the bottom of that to the bottom of our drive rail and make that 0.3125, which is 5/16 of an inch. Okay, and so that positions everything completely. Let's punch back in. I believe it was 335 for the 170 tooth belt. Let's see what that does. I want to be able to measure. I'm not super comfortable with that. Okay, let's go back to what it was. Also, SDP sells other sizes of belts, so you don't have to buy them from Vex. We could get a 165 tooth or 166 tooth. Well, let's look here. The ones that have that don't have an asterisk are standard sizes. So yeah, we can get 165, 166, 167. We can't get 63 or 64 outside of custom. But yeah, but typically I don't care enough to order belts from them. However, if you really feel, if you're really attached to the position of your wheel, or you're designing a mechanism that has to have a specific size of belt, then go for it. Really, shipping times are not a whole lot different. It's just a question of whether they have them in stock or not, and sometimes they don't. All right, so we've got a big gap here above the wheels. We want a little bit because there's just going to be a flange and stuff on the inside. We just want to make sure that there's enough room above the wheels that any fasteners that are hanging down from superstructure or whatever don't interfere. Just, you want to give yourself a little bit of headroom, but you kind of want to minimize the space. So like I said before, I think we ended up with 3.5. We could go, you want to go in 1/2 inch increments. I'll explain why in a bit, but if you go 3, you couldn't get away with this, but it's a little close. So, yeah, we'll do 1/2. This wheel's actually end up sticking up above, which, once again, technically not actually an issue. There wouldn't actually introduce any interferences, but it's more about when you put a superstructure on this, you want to be able to just bolt stuff across the drive rails and not have to worry about running into wheels or belts or anything. So that's kind of where we're at. All right. So this is done. We just need to add in holes for the shafts. These aren't bearing holes. They're just clearance holes for spacers, basically. So we're going to make them 1 inch. I think in the in-person class I had them make them 1 1/8. Actually, yeah, we'll go 1 1/8. 1 1/8 is the size for a bearing. You don't really need it to be that size, but it's kind of convenient to standardize for that hole size. Also, if we had to do something weird where we ended up needing, like halfway through the season, to put a bearing in there, not having to try to drill that hole out to 1 1/8 would be nice, so we're just going to use a bearing hole. Okay, so finish the sketch. Now we need to change our sheet metal defaults, make this 1/8 of an inch. I have yet to set up templates for this, but it's okay. All right, we're going to do a face. We're going to click that. We're going to click OK. So now we know it's 1/8 of an inch thick, and we got our face. We're going to change the material. Go to Autodesk Material Library. Scroll up to aluminum 5052H38. Now we're going to add flanges. Now we're going to add a flange on the front, the bottom, and the back, or the front, top, all 4 sides. Words. Okay. There, and there. All of the flanges need to be facing towards you. That's important. All right, so the flanges are going to be 1/8 of an inch from this front edge of the flange to the back face of the part, which is really hard to see. Basically, from here to here is going to be 1 inch, which is what we want. So that's measured. That's this height, the first height datum option, bend from the intersection of the 2 outer faces. So that's measuring from the outside. If we picked this one, it would be measuring from the inside, which is not what we want. So first option, we want the outside of the bend face to be flush with the edge that we picked, which is default. Our bend radius needs to be 0.146. That's just what our tooling does for 1/8 inch. Like I said, we might be changing machines and making some changes, so this might change for Stellar Robotics specifically. If you have a sponsor do this, you've got to get with them and figure out what the bend radius is for different thicknesses of material and put it in right, because it affects your flat pattern slightly. All right, we're going to click OK, and we're going to go back to the home view. All right, so this is pretty much it. Oh no, I made a mistake. Okay, I told you to do something wrong. Okay, so let's go back to sketch. When I did this square here, that was supposed to be on the middle wheel because the middle wheel is lower, right? So if we do this, the middle bearing block will interfere with the flange. So actually what we need to do is delete this dimension. You can delete the rectangle too, but I'm not going to bother. We're going to turn on construction geometry, go to a center point rectangle, find the center of this. We're going to do a 1.5, press the tab key, 1.5, press the enter key, dimension, and this is supposed to be 0.3125. I noticed that hole looked a little close. That was how I noticed that. It's okay. All right, so now we know we're going to have bearing blocks on here. Well, let's give this a save first of all. Save, fall. I have a drivetrain folder. I just want to look. What did I call this? I guess I'll just call it actually, I completely missed. I'm trying to name these consistently. It's, yeah, SR, yeah, it's the normal Stellar thing. All right. I'm just going to call it CAD class D for drivetrain. I can't do, well, I could do DT, but I'm not going to. All right, and then this is just going to be part 1. All right, so now we need to model a bearing block. Before we can put in here, we got to figure out the size the bearing block is going to be. So let's create a new standard part. Now we know it's going to be a square, and we know it's going to be 1.5 inches by 1.5 inches. We know it has to have a bearing hole in the middle, which is 1 1/8 inches. So let's extrude this out. No, not 1/8 of an inch, 1/4 inch. All right, so next we're going to create a sketch on this face here. Now we've got to position our bolt holes. We've got to be a little careful because we're really tight on space. So basically, we're going to have a center point rectangle, and our holes are going to be on the corners. But we got to evaluate this. So what I'm going to do is I'm going to take this is going to be a square hole pattern. So I'm going to just take an equals constraint from one side to the other to make this always a square. That just takes out some constraints later. Okay, so basically on the inside drive rail, we're going to have the flange of our bearing and the screw heads on the same side. Now the flange of the bearing is 1 1/4. The bearing is 1 1/8. The outside of the flange is 1 1/4. The head size of a 1032 screw is 5/16, 0.3125. So essentially, we're going to have the flange and we're going to have the bolt head on the same side of the part. So ideally, we don't want the bolt head hanging off the edge of the bearing block just because you're sacrificing strength, and there's just no good reason to do that. Ideally, we want this situated kind of like, we don't want to be hitting the flange, we don't want to be up against the flange, we want a small gap, so ideally we're somewhere about there. So let's just dimension this, and we'll pick a fractional dimension that's really close. So this is 3/16, 0.1875. And yeah, and that gives us the whole pattern that I was expecting that we used on the other part. Like I said, we've used this design before, so a lot of the numbers and things we've just kind of worked out ahead of time. So I'm just putting these in. Okay, so now we got to add 4 points before we can add our holes. These are going to be clearance holes for number 10 screws. Finish the sketch. Hole, click the hole feature. They're going to be clearance holes, and the size will be number 10. We're going to want to make sure it's going through all, which it is by default, so we're good. Click OK. All right, so now we're going to just add some small fillets on the outside. The default is 1/8 of an inch, which is good for us. That's what we want. So we'll just add some fillets. All right, so that's done. This is also going to be 50/50, aluminum 50/52 H38, probably. Depends on what we buy for the season. We might buy 60/61 plate for this because we're not going to be bending any 1/4 inch material. But that's besides the point. All right, we're going to save this. Yeah, something's going on with my Google Drive, but that's okay. I don't need it to sync while we're working. All right, so we're going to just click on this part. We'll just rename it to be the next number in the line, which is 2. All right, so now the big thing that we needed to know here, I'm going to press the M key to bring up the measure tool. We just wanted to know the distance between these holes, basically, which is 1 inch and 1/8. And because it's a square, it'll be the same vertically. All right, so going back to this, let's create a sketch on this inside face. See, this is the problem. See, the problem is it won't come up. Let's do a good old task manager here and see if I can kill it. Problem is I don't know what it's called. Google Crash Handler, Google Drive Sync. I'm going to assume it's that. Alright, am I going to regret killing this? Probably. Am I going to do it anyways? Yes, I am. All right, is it here? It's gone. Okay, so that might solve that problem. Let's try to give this a save. Yes. Okay, that worked. All right, good deal. All right, going back to the sketch. Sorry about that. Okay, so what we need to do is we need to place hole patterns for each of these 3 holes. So we're going to turn on construction geometry, click project geometry, and project each of these holes into our sketch. Next, we're going to pick a center point rectangle, and we're going to go, and this rectangle is going to represent the whole pattern itself. So it's going to be 1 1/8 by 1 1/8, and then we're just going to place rectangles down in the other places, and then just use an equals constraint to make the 2 sides equal, and then we'll just equal the tops. Okay. And actually, I'm going to delete that dimension and use an equals constraint here too. So I'm just clicking on equals, and then I'm clicking on one and then the other. It makes those 2 equal, and then I can keep clicking, right? So I can click, as long as I'm clicking in pairs, it's okay. So now I'm going to place center points. We should got to place 12 of them, 1 on each corner. Technically, you don't have to do this. You could pick the corners of the rectangles in the sketch using the hole tool manually, but really it's kind of a wash whether you put the center points in or do it in the whole dialog. We never talked about how to do that in the class, but this is the way I prefer to do it. It's more stable. Okay, so now we finished the sketch. We're going to click the hole feature. Now these are going to be tapped, so we need a tapped hole. They're going to have threads in them, is what I mean. Okay, so under the size, it's going to be a number 10. You have to scroll up to it. The designation is going to be 1032. Class is fine. Through all, check full depth. Not that it really makes a difference in our particular case. Then click OK. So you can see it puts this like hole texture in there. Now Inventor doesn't actually model the threads. This is just a texture on the inside of the hole, which is kind of annoying, but it doesn't hurt anything. Okay, so this is where we're at. So let's leave off here, and let's model our rear channel. So we know that this is 3.5. I need to think about something really quickly. We might need to move the wheels up a bit. I'll explain why we need to do that in a second. I moved the wheels up by a 1/16 of an inch. I don't have a good way to show you guys why that is, but I will show you guys shortly. All right. We were modeling the front and back channel. So we're going to go to sheet metal. We're going to create a new part. Basically, we're going to create a rectangle that's the same height as the drive rail, so 3.5 inches, and the width, the full width of the robot, which is going to be 25.5. Oh, whoops, I did that backwards. This is 25.5, and it's 3.5 inches tall. Okay, so next we're going to finish the sketch. We're going to change our sheet metal defaults to 1/8 of an inch thickness, face, click OK. Alright, so now we're going to have a flange on the top and a flange on the bottom, and those are going to wrap around the drive, or the drive rails. So we're going to click the flange tool. We're going to model this facing away from us. It doesn't really matter, but that's the way we're going to do it. Okay, now these flanges are going to be, typically what we do is 2 inches from the back face to the end, which is this height datum here, the first height datum. That's 2 inches. Bend radius, oh, I changed this to the wrong material thickness. So the bend thickness for 16th material, we'll change the thickness here. 16th material is 0.039. One other thing, basically the drive rail is the same height as this plate that I made, and we need these flanges to go on the outside of the drive rails, so we need to position the flange not here, because we want the inside to be even with the end of this plate. So it's going to be that one, just like that. Not this, not this, that. Okay, and that does the same thing on the bottom. So click OK. Go to sheet metal defaults, change this to 0.0625, which is 16th, and there we go, we're right thickness now. Alright, so let's change the material. Autodesk Material Library, scroll up to aluminum 5052 H38. We're done with this for now, so we're going to give this a save. It'll be the next one in the series, which is 3. Alright, so now we got to start an assembly. Yeah. New assembly. Go to the home view. Alright, so I'm going to place, we're going to start with the channel. This is going to be the, I guess we'll call that the front. So I'm going to rotate this around. This will be the front and this will be the back. It doesn't really particularly matter. That's just how we usually model it. Place grounded at origin and rotate another 180 degrees. So this will be the back of the drivetrain. Alright, so now we got to get a drive rail in here. So we're going to put this drive rail. Oh, right, the appearance is really weird. Well, it's fine. Okay, it didn't hurt anything. Interesting. Okay, so now we know that the end of this drive rail just goes right in here, and we know that the edges of these flanges are all flush with the end of the end channel. So we're going to go to the constrain tool. We're going to constrain the end of that to the inside of that. Wow, that was loud. I'm going to turn that bad boy down. Nearly blew my eardrums out. Okay, click apply. Alright, so then we're going to constrain the top of this to the inside of the flange. I'm doing that for a reason. It's still kind of loud. I hate that sound. Alright, I'm doing it to the top for a reason, so make sure you do it to the top as well. Then we're going to switch to a flush constraint. We're going to click the end of this little flange in here. And not the inside of the part, but the end of the flange, and then flush that to the end like that. Okay, and I'm actually going to switch to view edges, so we have some edges. That'll make it easier to see on the video. I think my modeling in that environment, I just need to assemble. Okay, so then we're going to kind of do the same thing on the opposite end, except this is fixed, because this part here is grounded, this part here is fully constrained, and this part here is not constrained at all. So we're going to go back to, oops. Which one is it? No. Yeah, up and to the right. Okay, so the inside of this part to the end flange there, the top of this to the inside of that, and then we're actually going to flush this channel here to the other channel, just because that makes more sense. Alright, so we're already taking shape here. I'm going to go ahead and end the video here. Next video, we're going to work on the inside drive rail, which is slightly different. We're going to add rivet holes to all this stuff, and we're going to mirror this on the other side. And we'll get bearing blocks in there and stuff as well. So thanks for watching. Stick around for the next one.